Alright, here we are on the fourth video in Math 208, and I'm going to start you off with this question: what does the equal sign mean in an equation? And I ask this to you because here's a typical algebra problem, algebra 1 problem: 3x equals 6, divide both sides by 3, and you get x equals 2. Sometimes I will have students come out and say, well, I got 2 equals x. Maybe they're doing a word problem and they started off with 6 is equal to 3x. That's how they wrote out their equation and got 2 equals x. And so their question is, are these two the same? Could they write it like that? And my answer is yes, it is. And there's a property for that we'll talk about later. But another thing is, students a lot of times want to say that the equal sign means the answer is. And it doesn't always mean the answer is. If I have the circumference of a circle is equal to 2 pi r, there's not really an answer there, it's just an equation. It means that the circumference is the equivalent of taking the radius times pi times 2. So it means an equivalence there. And so it's important that as we write out equations as far as teaching it goes, if you become a teacher, make sure that you don't always write it as the answer is always by itself over there. Sometimes write it out as 6 equals 3x. And throughout this course, even though this course is all about math and not really the method of teaching it, I will drop in some hints because, or some strategies for teaching occasionally, just because I think it's, a lot of my students are future elementary, middle school teachers or future math teachers. So just some things that I see as a high school and college teacher for my students coming up, that, a few things that the elementary, middle school teachers and other teachers prior to me could do to really benefit their students. All right, so today we're going to review some of these properties that you learned back in algebra or pre-algebra. And once again, these are things that I remember when I first took algebra I thought were ridiculous. Like, why do we even learn these? But then as I furthered my study in math and I became a teacher, I said, oh, these make sense while we talk about these. So it's one of those things that as a young student, I didn't understand why we did it. I just said, okay, this is just what's in the books, or the teacher's teaching it. But as I became more mature in mathematics, I understood, like, oh, there's a reason behind all of this silliness. So the first one right here we have is the commutative property of addition. It just says that if you have 5 plus 8, that is equivalent to saying 8 plus 5. So the order for addition does not matter, okay? Notice we also have it for multiplication. If I say 3 times 7, that's the same thing as 7 times 3. It doesn't matter the order that I multiply things. Notice our next property, though, is talking about the associative property of addition and then one for multiplication. What did we leave out here? There is none for what? The opposite of addition is subtraction. So the commutative property here does not work for subtraction. If I say 5 minus 8, does that equal, I'll put a question mark above it, does that equal 8 minus 5? Well, 5 minus 8 is negative 3 and 8 minus 5 is 3, so no, it doesn't. So there is no commutative property for subtraction. Same thing with division. If I were to say 21 divided by 3, does that equal 3 divided by 21? No, it doesn't. One's a fraction, the other comes out to be a whole number 7 there. So there's no commutative property for multiplication. Now, when I first learned these, they all seem to kind of run together and we start throwing out all these unfamiliar words. I remember that I learned it by saying when we commute to work, we go back and forth to work. So I kind of think of it as these go back and forth. It doesn't matter the order there. They go back and forth. Now, the associative property of addition, let's suppose we're adding several numbers, like 3 plus 5 plus 1. Now, when we follow the order of operations, we might, we're going to do parentheses first. So let's group the 5 plus 1 and say, do that 5 plus 1 first. Associative property says it doesn't matter which way I group these if it's all addition. So I could say 3 plus 5 first if I wanted to, and then add the 1. Same thing with multiplication. If I turn all these addition signs into multiplication signs, remember in algebra, a lot of times we use the dot for multiplication. it doesn't matter which way I group these to begin with. I'll get the same answer. So it's closely related to the commutative property, just associative. You think about when you associate with someone, you're being grouped with those people. It doesn't matter the way we group them with those parentheses. Notice once again, we've got it for addition, we have it for multiplication. We don't have it for subtraction or division for the same reasons, because the order a lot of times will affect it. So it's just for addition and multiplication. Then we have the distributive property. Now the distributive property, once again, is one that, okay, we use a lot in algebra. Like, let's suppose we have 3 times 5 plus 2. Or actually, let's make this, let's put a variable in it. Let's do 3 times 5 plus x. So 3 times 5 plus x. Distributive property means we draw what I like to tell my algebra students, swoopties. They love to hear that term for some reason. It's a made-up term. It's not a math term. But you draw these swoopties, and you say 3 times 5 is 15, 3 times x is x, 3x I mean. So you get 15 plus 3x, and that's using the distributive property to simplify that expression. The reason why I make a big deal out of drawing swoopties and saying a silly word is a lot of students will want to say this is just 15 plus x. They'll forget to distribute that 3 to the x there. So I always make my students draw those swoopties, especially when they're first learning it in Algebra 1. So you can do it over addition. You can also do it over subtraction. So you could have like 5 times y minus 2. And once again, we're going to draw our swoopties. And then we end up with 5y minus 10. And there's your answer there. 5 times y, 5 times negative 2, you get negative 10 there. And so that's what I was taught in Algebra 1, and that was great. I said, okay, and I used it a bunch for solving equations, but this also works out to be a useful tool for mental math. We talked about mental math in the last lesson. Let's try doing something like multiplying 5 times 99. Do that in your head. So doing it in your head, if you do the traditional algorithm, I can't do the traditional algorithm in my head, but some of you might be able to. 5 times 9 is 45. 5 times 9 is 45. Add them up and you get 495. So you have to do all of that in your head, which is confusing to me. So this is how I do mental math for something like 5 times 99. I say, you know what, 99 is really close to what nice, pretty number there? Well, 100. But how far off from it is 100? How do I make 100 equal to 99? I'm going to subtract 1 from it. So this is the same thing as saying 5 times, in parentheses, 100 minus 1. And so I can do that in my head a lot easier. I can say 5 times 100 is 500. Push that off to the side for a second. 5 times 1 is 5. And I know what 500 minus 5 is. It's 495. So that's all done in my head a lot easier. I think I may not picture this in my head, but I say 5 times 100 is 500. But wait a minute. I need to subtract 5 from it. Same thing with something like 5 times 98. Can you do that in your head fast now? Well, that's the same thing as 500 minus 10, which is 490. And so it allows me to multiply sometimes numbers like that a lot faster. You can do the same thing if it's something like 5 times 101. You could look at it as 100 plus 1 times 5 and get 505. But for this one, I find it easier just to do traditional. I can do traditional algorithm in my head there, 500 plus 5, and multiply each one of those ones by 5s, and I get the answer. So I'm not saying when I show you these tricks, it's not always the best way to do it. It's just whichever way your mind works. But the distributive property, I found out later on, I thought about it, or I read it somewhere and said, hey, not only can we use it for solving algebra problems, but we can also use it for mental math and multiplying large numbers. Then we have the additive identity property here. So for addition, and the world that we know with real numbers here, if I have the number 5, what number do I add to 5 to get 5 again? What can, like, if it, does 2 plus 5 give me 5? No. Does negative 3 plus 5 give me 5? No. The only number I can add to 5 and still get 5 is 0. So for our number set that we're using here in this class, the additive identity property is going to be adding 0. The additive inverse property. Now, this goes back, let's have the number 5 again here. What can I add to 5 to give me 0? Like 2 added to 5 won't give me 0. Negative 3 added to 5 won't give me 0. No, I have to add a negative 5. When I add negative 5, that's when I get 0 there. So the additive inverse is saying, what does it add up to give you 0? Or you might have learned in algebra, like if you got something like 5 plus x equals 3, you use the additive inverse to solve this problem. You might have learned to subtract 5 from both sides. You're doing the opposite of 5, or adding 5, which is subtracting 5. You're using the additive inverse property, and you're doing it to both sides. So 5 minus 5, you might have learned cancels, and I say that with quotation marks there. It cancels it out, but really what it's doing is it's adding up to 0. So when it adds to 0, you get x, and adding these, you get negative 2 to solve for your problem there. But that's when we use the additive inverse property. We have the multiplicative identity. Remember, look for that key word there. Is it identity or is it inverse? So the identity is saying, what do I multiply? Let's pick a new number here, 7. What do I multiply 7 by to get 7? That's a bad 7, so I'm going to redraw it. I'm going to multiply it by 1. So when I multiply by 1, I get 7. So for the additive identity, it's 0. For the multiplicative identity, it's 1. Once again, I've always felt like these were silly things, like when I learned them. But then when you take an abstract algebra course, which you're probably going to do if you're a math major or going to teach high school math, but as you take those courses, these become important properties. And so they're really setting you up for further studies in mathematics when they talk about these identity problems. Now the inverse properties we use a bunch because we're using them for solving equations. So if I had 7x equals 21, how would you solve that problem? Well, if you remember your algebra, you'd say divide both sides by 7 and you get 3. Well, if I take out that word divide, let's suppose we don't divide both sides by 7 and I say you have to multiply both sides by something. What would you multiply both sides by? Well, if you multiply both sides, some students might say 7. Well, if I multiply this side by 7, I end up with, here's my mental math coming in, so here 147 equals 49x, because 7 times 7 is 49. I don't get x by itself. So it's not 7. What is it that we need to multiply both sides by to get x by itself? That number that we're multiplying both sides by is going to be our multiplicative inverse to 7. Or another way to say all this is, what do I multiply 7 by to get 1? And I'll give you a hint. It's going to be a rational number. All right? It's not going to be a whole number or anything like that. It's got to be a fraction. So as we learn about multiplying fractions, we're going to learn that 1/7 is going to be our answer here. Because 7 times 1/7, remember, we'll make that a fraction by putting a 1 under it. And when I multiply the two, I multiply straight across the top and bottom, and I get 7 over 7, which equals 1. So I multiply this side by 1/7, multiply this side by 1/7. That becomes, it cancels, right? You learn that term canceling. What it's really doing is you're multiplying to get it to be 1. So you get 1x, or just x, equals 21. You make him a fraction, 21 over 7. And 21 divided by 7 is 3. We'll review these once again when we talk about rational numbers and multiplying them. And so if you're a little confused about all this fractional work here, don't feel too overwhelmed. What I really want you to know is just that the multiplicative inverse is basically just taking the reciprocal of that fraction. So 3 over 1, the multiplicative inverse is flipping that fraction, 1 over 3. 5 over 8. If I flip that fraction, I get 8 over 5. That's the multiplicative inverse. You multiply 5/8 by 8/5, you're going to get 1. All right? So we'll discuss more of that and more examples as we talk about rational numbers. Now, in your resources, I've got, for this week, I've got some number cards listed. So I want you to get out those number cards, have them printed out, cut them out. If you don't have a printer, really all you need is some pieces of paper. You can cut out your own pieces of paper and write these numbers on it. I've chosen just these numbers for today. And so you pick out those numbers. Now, if you want to do this exercise some more, you can pick out your own set of numbers and play around with them. And so for right now, what I want you to do is take these 6 numbers here, and I want you to arrange them into 2 3-digit numbers, like this one right here. And I want you to take the sum. So if I add these right here up, 7 plus 8 is 15. We're just doing traditional algorithm right now. 6 plus 6 is 12. I end up with 525. Now, I could arrange these a different way and get a different sum. So if I put the 8 over here, whoops, they're not tied together like I thought they were. If I put the 8 over here and the 3 right there, now when I add them, what do I get? I get, carry the 1, 2, carry the 1, I get 1020. Now, what I want you to do with using these 6 numbers is I want you to come up with the largest sum possible. You can even rearrange these so that, you can move the 6 up top if you want to, and the 5 down below. It's another one that's not together. So however you feel like you need to rearrange these, rearrange them to get the largest sum possible. And then I want you to see, is there another way you can rearrange them and still get the largest sum possible? So pause the video and try that out. All right, so hopefully you paused the video and you kind of went through some of these. I've written down my answers here on the right. The largest sum I could get was 1614. If you got something different, let me know, because but as far as I'm concerned, I'm pretty confident in that answer. And my strategy for doing it was probably the one you discovered, was that we needed our largest number in the hundredths place. So I moved the 7 and the 8 all the way over to the left, and then the second 2 largest numbers need to be in the tens place, and then my smallest numbers are going to go in the ones place. So when I do that, this is the first addition problem I came up with. I got 7 and 8 hundredths, and then 6 and 5 tens, and then 1 and 3 ones there. Adding them up, I got 1614. But that is not the only 2 numbers here I could, or two different numbers I could make to add up to 1614. I could switch the 7 and an 8 and have 861 plus 753. Or I could take this original one here and switch just the 5 and the 6 and get 1614. And so I end up getting 6 different sets here that I could add up, 6 different pairs of numbers that I could add up to get 1614. And so you should have gotten something kind of like that, maybe not in the same order, maybe that wasn't your first that you wrote down, but yours should be listed there. Now, I want you to take the same set of numbers here, and I want you to use subtraction this time. And our rule is we don't want any negative numbers, so this setup would not work for us. We want just the whole numbers. And I want you to subtract to find the smallest difference that you could make and write out as many possible ones there. So for instance, I said we'd have to switch the 1 and the 8. Let's ungroup this. So if I switch the 1 and the 8, now I can subtract and get a number that's not going to be negative. And I get 4, 1, and a 7. Is that the smallest number I can make that wouldn't be negative? You pause the video and find out. Move those numbers around and see if you can come up with a strategy and write out as many different ways that you could do that subtraction problem. All right, now I'm not saying that this is the answer. I haven't completely worked out this problem yet, but I want to show you that it's not quite as easy as adding, because adding, we know we can get just the biggest numbers over here on the left, the second biggest in the middle, and the smallest numbers on the right, and you get your sum pretty quickly. Now, my strategy for subtracting is to first try out all the numbers that are really close to each other, like 8 and 7, or one digit away. If I can do that, if I put the 7 up top, I'd get a negative number. 7 minus 8 is going to give me a negative number. So I have to put the 8 up top and the 7 in the bottom. And then I want the smallest number of right here next. You know, you got 8, 7, and the smallest number goes right there. And then the next smallest right next to it, because I want to make that number on top as close to the number on the bottom. So this number needs to be minimized and this one needs to be maximized. So I put the next to the largest between 8 and 7 there, or after 8 and 7, right here, and then the third large, or the fourth largest out of all the numbers right here. So when I subtract these, we're going to get, let's see here, if we borrow a 1 right here, this is using the traditional algorithm, I get an 8 right here. Subtracting these, we're going to borrow again, and I get a 4 right here. So I end up with 48. Now, that doesn't mean it's the smallest one. I've got to try a few others, but I'm going to write it off to the side. I've got 813 minus 765 gives me 48. Okay? Now, I'm going to pause this video and set this up a different way. Notice the 6 and the 5 could be rearranged so that you have it like this. So let's move this box over. I group these and then they ungroup when I'm dragging them around. I don't know why it does that. And so I don't even have to pause the video. We've got it set up now. So once again, these numbers are only 1 unit away. And then I've got the smallest number next, and then the next smallest number, and then the largest number here. And I'm going to subtract those. So we haven't talked about mental math with subtraction yet, but I'm going to do some mental math right here. So we'll have that example taken care of. I know that 600 is a number in between 613 and 587. So I know that I'm 13 away from 600 right here. I'm 13 away from 600 right here. Adding these up, I get 26. So the difference there is 26. You could still do it traditional. Borrow the 1. I say that with quotation marks there. 13 minus 7 is 6. Borrow another 1. You get 10 minus 8 is 2. You get 26. So that one's actually smaller. 613 minus 587 gives me 26. So that's why you've got to play around with the numbers a little bit here with subtraction to make sure you're getting the smallest possible number. Now there's one more set. So we did the 8 and the 7, the 6 and the 5. We could also do the 6 and the 7 here. So let's try rearranging that. So here, once again, I've got two numbers I can subtract, and that's as close as I can. It's the smallest number I can make in the 700ths, and that's the largest number I can make in the 600ths. And I'm going to do the mental math again. A number in between is 700. This one's 13 away. This one's 15 away. When I add them up, I get 28. So those are 28 away. 713 minus 685 is 28. Still, this one gives me a smaller number. I don't see any others here. We got 7 and 6, 7 and 8, 6 and 5. There are no others that are just 2 units away. I mean, 1 unit away. If I did 3 and 1, I know the difference is, you know, if I made 300 something minus 100 something, it's going to be bigger than 20 something there. So this is going to be my answer. Now, with that being my answer, 613 minus 587, let me put that back up. 613 minus 587. There's no other way here that I can subtract these or rearrange these and get 26. See, with addition, I could switch around these numbers and add them and get the same one. But if I switch around the 3 and the 7, I'm going to get a different difference here. So, for instance, move the 3 and the 7 around, and my difference is not 26. It's going to be, it's here, that's going to be 4. Here, we'll subtract it out. That's 4, borrow the 1, and you get 34, which is not 26. And so there's a couple of goals to this exercise. One is to make you think about place values and where to put which numbers into the hundredths place and the tens and the ones for the greatest sum or the smallest difference. And the other is to reemphasize that addition is commutative. The order that we add them can be switched around, which gives us more options when we do the addition part. However, subtraction is not commutative. The order does matter, and so our answer will change depending on how we arrange the numbers. Now, next, I put this in here just as a reminder. We talked about in the last video that the closure property. Remember, for addition, closure property is saying, if we're talking about just the whole numbers, if I add 3 plus 4, they're both whole numbers, that's what I'm adding, do I get another whole number? And I do. But if I were to subtract 3 minus 4, do I get another whole number? And so 3 minus 4 equals -1. -1 is not a whole number, so the closure property does not hold for subtraction over the whole numbers. So just a reminder there, we talked about in the last video, but sometimes I bring up things again just to kind of, as you know, we see the general overview, but as we get into more detailed things, specific things, you can see or be reminded of what's going on. As far as middle math with subtraction goes, you're a little bit more limited than what you had with addition. But I think the biggest thing here is what I've already shown you. If I'm doing 34 minus 23, in my head I'm thinking, what's a number in between those two? And I say, okay, 30. And so 34 is 4 away, and 23 is 7 away. So if I add up that 4 and that 7, I get 11. This one's easier to do traditionally. And traditional algorithm just says subtract, subtract, and because these two digits are larger than these two, it makes it pretty easy. Let's try one where it's not so easy. Let's say we had 78 minus 59. So in this case, the traditional algorithm says to say borrow, and I say that with quotation marks, a 1. You're really borrowing 10. Make that a 6 and turn that into 18. You get 19. 9 and then a 1 there, so 19. If we're doing it the other way, where we pick a number in between, you can pick 60 for this case. You can do 70 as well. But if I pick 60, then I say, okay, 59 is 1 away from 60, and 78 is 18 away from 60. Adding up those two red numbers, I get 19. And that's a little bit easier than trying, at least for me, trying to borrow a 1 in my head and keep up with it all. I just pick a number in between. 60 is super close to 59. It's only 1 away. And then you're at 18 away from the 78 there. So those are some middle math subtraction strategies. We can do subtraction over a number line here. So if I was subtracting, let's say, 8 minus 3, this is how I want you to do it. Once again, we said before, start at 0 and go all the way out to 8 to show me a positive 8. And then subtract from it 3. So when we subtract, we just say go in the opposite direction. So I subtract and go 3 this way, and I end up at 5 as my answer. So make sure you start at 0 in all of these. That's going to be extremely helpful when we start subtracting negative numbers, and that to have that foundation where we start at 0 always. Then we have the chip charge model. Now the chip charge model I love for using with negative numbers, like when we subtract negative numbers, but I'm going to go ahead and introduce it to you now, so that way we're all set up. So let's say we had 5 minus 2. And I want to show this with the chip charge model. So 5 minus 2. The key to the chip charge model is that we want to be, when we're subtracting, we want to be taking something away. So I've got 5 here. And when we start talking about negative numbers, you don't have to color yours in, because I know you probably just got a pencil. If you want to, you can. Or you could actually just take, for the online course, you could just take pictures if you've got like red and yellow counter chips, you could use those as well. But you can use these plus symbols for positive numbers and minus signs for negative. I'd go ahead and do both because it's easy to do on the computer. But just to show something like 5 minus 2, you start off by showing that you got 5 there. That's a positive 5. And then we're going to remove 2 of them. Okay, so we remove 2, and this equals 3 positives. So I want to see the whole thing drawn out. Just don't write out 3 positives there, but show me that you started with 5, you remove 2. That's the best way you can really do it without making a video, actually showing you physically take away 2, and then that your answer is 3. And that kind of concludes just the subtraction strategies we'll go over. There's plenty more out there if you want to look them up. But like I said, it's a little bit more limiting just because of that commutative property of addition works, but doesn't really work for subtraction. So try these out on the homework. If you have any questions about that or the properties, let me know. And thank you for watching. Once again, hope you're having a great day and enjoying the class.